Hello, can you please confirm if I'm audible? You can write in the chat box if I'm audible. Okay, fine. So let's start the week 8 session, which is of the course Digital Electronic Circuit, which is taught by Professor Gautam Saha from IIT Kharagpur. So I'll give a brief introduction of myself. I am Anil Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving week 8 assignment problems and similar problems so that you can clear your concept better and we can have a good live interaction during the session. So this was the course outline that we have covered till now and that we will cover till now. So here you can see in week initial weeks that from week 1 to week 6 we have covered the combination circuit quite uh, well, and then from the last week, that is from week 7, we have started covering the most important topic of digital circuit, which is nothing but sequential circuits. So this is the most important topic in your competitive exams such as GATE, IES, etc. So I prefer that all of you should attend these live sessions regularly because I see a lot of students are not attending the session. So I'll recommend to at least see the recording of this video, which are available on YouTube, etc. So in the last lecture, we have covered the basic of sequential circuits, such as all the flip-flops we have covered, SR, which is set reset, delay flip-flop, JK flip-flop, and then toggle flip-flop, and all the triggering, etc. we have covered in the last lecture. And we have also covered the most important topic, which is the conversion of one flip-flop to another. That will help you in solving a lot of competitive problem. So in this week, as you can see, we have contents which cover most of the shift registers, which are nothing but I'll tell you the basic of it. What is a shift register through questions, obviously, and what are the basic applications of shift register, such as ring counter, Johnson counter, and these all will be covered in this week's lecture. And okay, so I'm not audible. Okay, wait. Is it like I'm speaking slowly or my volume is not properly audible? Like not at all.
Now it's fine, sir.
Okay, okay, thank you. So I'll repeat that the course outline again. Maybe you can mute your mic. Yeah. So in the course outline, what I have told that in the first 6 weeks we have covered the combinational part of this course, and from the last week we have started the sequential part, in which in the last week we have covered the SR flip-flops and different flip-flops, and how can we convert one flip-flop to another, basically, which is the flip-flop conversion. And using this application of or these different flip-flops, in this week we will see the applications of these flip-flops in terms of shift register, what is a shift register, and what are the different applications, how can we use them as a counter of different types, and one more, which is the very important topic, which is a LFSR, which is nothing but linear feedback shift register. So in this week we will cover this basic content. So let's start with the problem number 1. So I'll take few this year's assignment problem, few last year assignment problem, and few basic book problem of I guess I've taken from Maurice Mano. So let's start with the question number 1. So as you can see, the question says there is a circuit which has certain number of D flip-flops, and it says that let the initial state of the ring counter before the clock applied is 1010. So it is given that the initial state of the ring counter is 1010, which is indicating nothing but Q3, Q2, Q1, and Q0. Or I can say, wait, in the question, according to the question, it is nothing but Q1, Q2, Q3, and Q4. So I can write here the initial condition is nothing but 1010. And then the question asks that what will be the output waveform of the counter circuit. So it is nothing but a counter circuit. So, okay, I'll tell you the basic of it. What is a counter? So, counter is nothing but a combination of flip-flops, basically D flip-flops in series, and they all contain a single clock. which is negatively S triggered. Yeah, and we all have a cascaded D, and the last output is connected to the input of this. So these all are D flip-flops, and let's suppose this is Q1, this is Q2, this is Q3, and this is Q4. So these counters are nothing but kind of shift registers. Okay, I have not put the clock here. So what they do is they just shift the bit, and the LSB gets shifted to the MSB in the second round. So I'll tell you how it works in the second clock cycle. Okay, so I'll repeat again since someone else has got admitted. So basic counters are nothing but they are a series of cascade connection of different D flip-flops, and these counters are called ring counters because they are nothing but since the LSB is getting the output of the last flip-flop, which is the LSB is getting as the input, which is the MSB and which is the first flip-flop. So in the question, it is quite clearly given that initial state is nothing but 1010. So they are nothing but they just getting shifted. So if I write 1010, sorry, yeah, and this zero is getting shifted. Let me use some other ink. This zero is getting shifted to the first bit. So I can write zero here. Okay, it was one, and now again this what is happening? 010 will be shifted here, which is nothing but 010, and this one will get shifted. Let me use some other ink here. So as you can see, in this particular circuit, what it is happening is from 1010, it is getting 0101, and then it is again getting 0101. And this sequence will go on till whatever clock cycles we have used. So as you can see, the question says that the initial state was 1010. So it was given in the question. We have not assumed anything. So according to the initial state given in the question, what will be the output waveform of the counter circuit? So as you can see, there are only two possible answers. One is it will be continuously toggling around 1010 or it will be 0101. So we can see the waveform given in the question. So you can see here it is. So you can see here it is 101010. So here it is 1010 and then so on. So since we know that now this both cannot be the answer because they are giving some different state which are a long time zero and then so we have only two options which are A and B. So you can see the first output is nothing but initial state was 1010. So if I try to match the answer, so it will continue always like 10101010. So you can mark either of the answer, but the most correct answer would be this because the initial state was given as 1010. So if I try to give you the correct answer to this question, it will be option number B. Is it fine? Do I need to repeat it? If you have any query, you can type in the chat box. I hope it is clear. It was quite basic question, but I can repeat if you have any query. And please
Please
try to.
repeat once, sir. Please repeat once.
Sure, sure. So the question says that the initial state of the ring counter is nothing but 1010. So as you can see in the given circuit, I have taken 1010 as the initial state. And the ring counter, what it does is it takes the LSB, the which is the final output of the last flip-flop to the input of the first flip-flop. So what I am doing is I am just writing 1010 here. So I guess till here it is clear. And what it is doing is now if I write 1010 here, so what is happening is it is shifting all the bits to the right. So this one will get shifted here, this zero will get shifted here, and this one will get shifted here. So if I try to use some other ink, so this one will get shifted here, this zero will get shifted here, and then this one will get shifted here, and this zero is getting to the input of the first flip-flop. So this zero is getting shifted here. So it will
Okay,
now,
then the answer would be the first one, no, sir. After applying the clock pulse, 1010 will get converted to 0101.
yeah, that is what I'm saying. So if I try to analyze the circuit again, So 0101, it is again getting converted to 1010. I hope you get this
But that
part.
is a second clock pulse. But immediately after clock pulse applied, the next
Okay,
state
okay.
could be 0101.
Yeah, so what will be the output of the counter circuit? Yeah, so after first clock, the preferable answer should be option number A, but it has not mentioned. So you can, since there is some ambiguity in the question, can you please mute your mic? Yeah, so there is some since ambiguity in the question. So if it is saying that after just applying the first clock pulse, after just applying the clock pulse, then yes, the answer would be option number A. And that would be a better answer, I guess. So I hope you are correct. So I'll also prefer if it is saying that just after the clock pulse, so the correct answer to this question will be option number A only, which is 0101. I guess this is year's assignment problem, if I'm not wrong. I guess they are also preferring option number A, if I'm not wrong. Is it fine now?
Okay, okay, sir.
Yeah. Okay. So maybe we can get to the next question now, which is a similar question to this. Maybe you can try this question by yourself. So it says that in the following circuit, consider initial values of the all the flip-flops to be zero. So I'll give you a hint. Initial values of all the flip-flops are zero. That means Q1, Q2, Q3, and Q4 are zero. And it is saying the output will again be zero after how many clock cycles. So it is quite a basic question. It just requires some
Four,
combination.
four clock pulse.
Okay, so we'll check. Or others also you can try the question and we'll check that how after how many clock pulses it is getting zero. So I'll give you 2 minutes and then I'll try to solve it by myself. I've got one answer as four, so I'll write that.
So 7.
Okay, I've got seven as second answer. Okay, I'll give you maybe 2 more minutes since you are getting different answers. So maybe you can recheck your answers and then tell me what is the final answer, and then I will try to solve the problem. Okay, so yes, there is no other answer, so I'll check which is correct from 4 and 7. So it is given Q1, Q2, Q3, and Q4 are initially 0, 0, 0. So we'll see that when it is getting 0, so you can see clearly in the circuit. So let me try to analyze. So this is nothing but this Q4 bar is coming here, and this is nothing but Q3. So next Q1 will be nothing but Q3 XOR Q4 bar. And then Q2 will, these all will be same. These all will just shift and the last will be changed to some other value. So let me try to make this as 0, 0, 0. And the last bit will be, now the Q1 will be changed to, it is nothing but Q4 bar, which is 1, and it is getting XORed with Q3, which is 0. So it will get 1. I hope this step is fine. Is it fine? You
Yes,
can
sir.
okay, fine. So now I'm just shifting these three bits. So it will be 1 0 0, and the last bit will be now it is Q3 XOR Q4 bar. So I'm writing 1, which is Q4 bar, and Q3 is nothing but 0. So it will be again be 1. So I'm just repeating the steps again and again. So it will be 1 1 0, and Q4 bar will be 1. Uh, and then it is getting XORed with Q3, which is 0. Yeah, it will again be 1. Now I'm doing the same step again, 1 1 1, which is this, and Q3 bar, so it will be 0. Q4 bar will be 1, and 1 XOR 1 will be 0. Yeah. Then 0 1 1, yeah, 0 1 1, right? And then 1, so it again be 1. If you have any doubt, you can ask or type in the chat box in the middle also. 1 0 1, and then last will be again 1. So I'm writing it again 1 1 0, then it will be 0. I'm writing 0 1 1. It will be 0. Then I'm writing 0 0 1. It will again be 1. Then I'm writing 1 0 0. It will again be 0. Okay, let me try to write here now. It will be 0 1 0, and since both are 0, so it will be 1 0 1 0. 1 0 1. It will be 0. Do we get something different? 0 1 0. So we are getting 0. So 0 0 1. Then we are getting 0. Then 0 0 0. Now we are getting 0. So I guess these two are not correct for sure. It is not 4 or 7. There are too many clock pulses. Let me try to count using this different thing. So after it was the initial state, so this was the first clock pulse, second, third, fourth, fifth, and then sixth, and then seventh. This is eighth, ninth, tenth. This was 11th, 12th, 13th, 14th, and then 15th. So the correct answer to this question is neither 4 or 7, so it is 15. Is it clear since both of you have not given the correct answer? Is there any step which I need to repeat in this question? You just need to analyze the circuit properly. Is it fine
You
or do I
repeat
need
it,
to repeat it?
kindly repeat it one more time.
Sure, sure, yeah. So as you can see from the given circuit, it is just a continuous shift resistor. The main point to grasp in this circuit is the Q1 bit, which is getting the input of D1. It is getting Q3, and it is getting XORed with Q4 bar. So you can see here, this is Q4 bar. I hope you know this basic of flip-flops. So Q3 XORed with Q4 bar is getting to the first bit of it, and rest of it are just getting shifted. So what I have done is if I repeat it, the first three bits are getting shifted. There is some participant. Yeah. So 0 0 0 is getting shifted to here 0 0 0, and then I am doing the Q3 XOR Q4 bar. So the first one will be 0 XOR 1, since Q4 bar will be 1. So this one will get written here. Now you see 1 0 0. So it will get shifted here, and the first bit will be Q3 XOR Q4 bar, which is nothing but 1 XOR 0, which I have written here. So the initial bit now be 1. Is it clear till here? Uh,
Yes, sir.
Fine. So now this 1 1 0 will get shifted here, and the next bit will be 0 XOR Q4 bar, which is 1. So 0 XOR Q4 bar will be here, which is 1. So I have written the 1 here. Now 1 1 1 will get shifted here, and 1 XOR 1, since Q4 bar we have to write, it will be nothing but 0. And similarly 0 1 1 will get shifted here, and similarly all the steps, and after getting so many calculations we have got final 0 0 in the 15th clock cycle. Is it fine?
Yes, yes.
Sure. Okay, maybe yeah, you can recheck or relook at the question, those who have given 4 and 7 as the answer. We'll proceed in 2 minutes once you'll grab it. If you have doubt, I can repeat the question again. You can ask in the chat box. Then let me, yeah, you just need to see this. This is the main point. Then the zero and zero is here. Is it fine? This is first. Okay, sorry. If you must. Shall I proceed?
Yes, sir.
Fine. So let's see this here. Okay. So this question says it has a concept of LFSR, which is nothing but a linear feedback shift register. So linear feedback shift registers are shift registers which basically shift the bits according to the polynomial representation of them. So here you can see it is given as x cube
Sir, you are
plus.
not audible.
Uh,
Hello?
is it the case with everyone? Am I not audible?
No, sir, you are audible to me.
Maybe Rajni, you can check your connection. Maybe it is from your side.
Rajmi ma'am, we can check your connection.
Yeah. Can you also confirm Santosh if I'm audible?
Hello?
Yeah. Hello.
Hello?
Am I audible? Jagannath, can you please confirm if I'm audible?
Yes, yes. Sir, you are
Okay.
audible to
So
me, but I
yeah. So
don't.
I guess the connection problem was from her side. So she will rejoin maybe. So I'll continue with the questions. So it says that it has a linear feedback shift register and it is getting represented by the polynomial representation, which is nothing but x cube plus x square plus x plus 1. So I'll tell you how to represent this. So first of all, you need to make the number of bits which are nothing but if it is represented by x to the power n plus x plus 1, let's suppose, and so on. Sorry, n minus 1, then n minus 2, and then plus 1. So you need to see that what are the corresponding bits. So you will always take the input as x to the power 0, which is nothing but 1. Then you will take the corresponding next to be bit. Yeah, you will take the corresponding next to be x to the power 1, then x to the power 2, then x to the power 3, then x to the power 4, and so on. So what we can see, the question says that a 4-bit LFSR. So first of all, I have make 4-bit. And then it says it has external feedback and which has the polynomial representation, which is nothing but x3 plus x square plus 1. So you can see it is getting x3 and x square added. So if I try to XOR them and just connect this. So what it is doing now, x cube and x square term are getting XORed and the last term which is 1 is getting added. So it is nothing but x cube plus x square plus 1. So this is the representation of following polynomial which is given in the question. So yeah, all right. This was the polynomial representation. So what we have done, we have XORed this x3 and x square together, which was the which was the second and the third least significant bit, and then we have XORed it with together with the one which was given in the last polynomial. Is it fine with all of you? This circuit?
Yes, sir. Yes, sir.
Yeah, sure. Now the question says that let the initial LFSR to be 1, 1, 1, 1. So let me write them as maybe PQRS. So if I try to write PQRS, which are initially 1, 1, 1, 1. And now you can see the relation for the first bit. All of them are getting shifted, but the first bit P, which is getting equal to, let me write it here, Q XOR R. Is it fine? Is it fine with everyone? Please try to respond if it is fine.
Sir, I didn't understand x power 2 and x power 3. If we give to XR, how it
Yeah.
will become x power 2 plus x power 3?
Okay. So, okay, I'll repeat again. So the question says it has a 4-bit LFSR, and the 4-bit LFSR is always represented. The input is always x to the power 0, which is 1. Then the first bit is always x to the power 1, then x to the power 2, then x to the power 3, then x to the power 4, and so on, whatever the bits may be. Now the question says it has a polynomial representation. It is given here, yeah. X cube plus x square plus 1. So this plus always represent XOR. Is it fine
Okay,
till here?
okay, okay.
So this x cube and x square are getting XORed. So if I try to make a circuit something, yeah. And finally it is getting connected to this one input. So this is how we make a polynomial representation into a circuit for LFSR. Is it fine now?
Okay, sir.
Yeah. So the question says that the initial bits are 1, 1, 1, 1. And you can see if I try to write them as again PQRS. So P is nothing but Q XOR R, right?
The output of XR is now 1, 1, 1, sorry, 0.
The output of R is, sorry.
XR. XR gate is 0 because even number of 1
Yeah,
is
yeah,
there.
yeah, exactly. So P will be in the next cycle, P will be 0, as you said, which is 1, 1,
Hmm.
1, and this all these will get shifted here. Is it fine?
Yes, sir. Yes.
So similarly, so let me ask you the question. So it says that the generated pseudo random sequence has a period. So period means that when will this 111 arrive again? So it will the period will be the number of clock cycles it is getting again. The input is getting same as the output. So let me try to give you this question. You can solve and maybe you can tell me how many clock cycles it is taking to cover the whole. The options are 7, 8, 15, 16. So you can go on and maybe tell me what is the answer. I can give you 2 minutes. Will you be able to do it?
Yes, sir. Yes, sir.
Yeah, sure, sure. Take your time.
There is a direct formula in the lectures are provided. That is 2 to the power n minus 1.
Okay. 2 to the power n minus 1.
So that we can get 7 answers.
Fine. Okay, so is it the case for any polynomial, or for this particular polynomial you are saying this formula is correct? Okay. I'm just trying to clear the concept of LFSR. So maybe you can try with this approach, which is more conceptual, instead of
Okay, sir. Okay, sir.
just, yeah, instead of just reminding the formulas. Okay. I'm getting one answer is 16. So one answer is 16. Anyone else? So you are saying 2 to the power n minus 1, which is 7, right? Any other answer? I'll give you 1 more minute. Shall I do it or someone else is also doing it? Rajani, you were trying.
Yes, I've taken all 1, 2, 3, 4, 5, 6, 7 clockworks, but still not reached that state
Oh,
one
fine,
one
fine.
one back.
Okay, fine. I'll do the question. Maybe you can check. So I'll do this 0, 1, 1 here, and then it is the first bit is nothing but q XOR 0, so it is 0. So I'm just doing 0, 0, 1. Then I'm getting 1.
Oh, why that leftmost bit is P is occupied by 0 here in the second step?
So I have just written that p is nothing but q XOR 0. So in the previous step, q and r were 1, 1. So
Okay,
they are getting
okay.
XORed and they are just getting here. Similarly, now
Oh,
0,
okay,
1,
okay.
1 will get shifted here,
Okay, okay, okay.
and then XOR of 0 and 1 will be getting here. Is it fine?
Yes, yes.
Yeah, so I'll write whatever I'm getting. So 0 is 0, then 0, 1, 0, then it is getting 1, 1, 0, 1, getting 1, and 1, 1, 0, is getting 1, then 1, 1, 1, is again getting 0. Did 1, 2, 3, 4, 7. Okay, I've done some mistake, I guess, maybe. So 1, 1, 1, it was 0. Yeah, these keywords are only. Then it is 0, 1, 1, and it is 0, then it is 0, 0, 1. It is again 1, then it is 1, 0, 0, it is 0. It is 0, 1, 0, and then it is 1. It is 1, 0, 1. It is again 1, then it is 1, 1, 0, again 1, then 1, 1, 1. And it is again 0. Okay, so 0, 1, 1, again 0, 0, 0, 1. It is again 1. Okay, it is getting repeated here. The last two bits. Okay, I've done something wrong, I guess. Yeah, yeah, yeah. Okay, okay. Cube, cube plus x square plus 1. So it is x to the power 0, then this is 1, 2, 3, 4. Okay, let me try to check the concept. Give me a second if I'm doing it correctly.
I don't think we'll reach to 1111 back.
Yeah, yeah,
In the,
exactly. Yeah, give me a moment. I guess I've done something. So 0, 1, 1, 1. Let me recheck my answers. 1, 0, 0, 1, 1. Then 1, 0, 0, 1. Then it is 0, 1, 0, 0. And then 1, 0, 1, 0. Okay, yeah, yeah, fine. So it was getting repeated here, I guess, right? We'll not get to 1, 1, 1, but we are getting it to 0, 1, 1, 1, which was this, right? Uh, can you understand this? That we had a 0, 1, 1, 1, and now it is getting repeated after certain cycles. Is it fine?
yes, sir, yes, sir.
So we are never getting 1, 1 again, but we are getting a circular period and we are getting these number of bits again. So now you can check 0, 1, 1, 1 and 0, 0, 1, 1, and it is getting repeated again. So you can check the number of cycles here. So it is nothing but one, which is the first clock, then second, then third, then fourth, then fifth, then sixth, and then in the seventh clock cycle we are getting the uh, clock again. So first, second, was third, this was fourth, this was fifth, this was sixth, and this was seven. Is it fine? Can you relate with the concept? Please respond.
Yes, sir, yes, sir.
Yeah, fine. So the correct answer to this question will be 7, not 16. Someone was getting 16 as the answer, so it was not 16, it is 7, which is option number A. Maybe you can check this question and then we'll proceed to the next one. I'll give you 2 minutes. So, someone was asking, shouldn't we ignore last two bits? Okay, what is the last two bits? No, the last two bits are x cube and x to the power 4. The polynomial given in the question is x cube plus x square. So we cannot XOR them. We should XOR this x square and x cube term. Yeah, sure, I'll show the question again. Yeah. Okay, let me clear it a bit. Is it fine? Can you relate now that how this has converted to this, not the last two bits? Santosh, can you please confirm? I can repeat if you're not clear. Sure, I'll repeat. So the polynomial representation is x cube plus x square plus x to the power 0, which is nothing but 1. So here I have written that for any LFSR, the input is always x to the power 0, which is 1, and then we add the corresponding powers to the corresponding bit. So the first bit will be x to the power 1, then second will be x square, then third will be x to the power 3, and then so on x to the power 4. Since it is given in the question, it is a 4-bit LFSR. So we have taken 4 bits. So 4-bit LFSR should have the highest polynomial of the order x to the power n, which is x to the power 4. So since it is 4 bits, so we are getting x to the power 4. Now the question has the polynomial of x cube and x square. So they are getting XOR together. So we should not XOR the last 2 bit, but we should XOR the x square and x cube term, which are the middle 2 terms. And then it is getting added to the initial term, which is 1. Is it fine? Okay. So if it is fine and you understood the concept, so maybe, okay, fine. Let me try to give you a question. Okay, let's solve this question first, then we'll go to the next question. So please try to understand this question quite attentively because it is a good question. So it says that determine the input to the JK flip-flop so that the circuit will function as an n-bit serial adder. I hope you know the concept of full adder and you know the what is the sum and what is the carry. So I'll write for you. So a full adder has three things, two inputs and one carry. So the expression is this: A XOR B XOR C, which where A and B are the inputs and C is a carry. And carry expression is, if I'm not wrong, it is AB plus BC plus AC. So now the question says that we need to determine the input of J and K flip-flop such that this circuit acts as an n-bit serial adder. So I hope you have attended the last week lecture. So it will require some conversion of flip-flop. So we have a JK flip-flop and we need to check the output of the we need to check the input of the JK flip-flop. And we'll do it by using these 5 major points that we always use to. Okay, I guess I lost my network connection. Let me. Am I audible, right?
Yes, sir, you're audible.
Okay, fine. Give me a moment. I guess I have lost. Maybe you can try. It is fine. You can try this question. I'm trying to reconnect with the laptop. Am I still audible? Hello?
Yes, sir, you're audible.
Sure, sure. Okay, fine. So have you got any answers? If you see here only. Okay, so I'll try to solve the question by myself. I'm getting the connection. So the question says that we need to check the input for J and K. So we'll check all the possibilities. So you can see here S is nothing but this X and this Y and this C out. It is getting into the sum which is XOR nothing but XOR. So we can write S as X XOR Y XOR C out. And you know for a JK flip-flop it is C out which is QN plus 1. And yeah, we don't really need anything else. So I'll write all the possible combinations. So if I write q and x and y, and qn plus 1 will be nothing but c out and sum. There are five things that we need to. Sum is nothing but x XOR y XOR c out, which is qn plus 1, and this c out is nothing but qn plus 1. So yeah, I'll write all the possible combinations now. So we know C out is nothing but Qn plus 1, and C out for a circuit is we know the relation. So we'll add accordingly. C out will be 0 plus, and then this carry is also 0. 0, this is 1, this is 0, this is 1, even this is 1. Is it clear that how I have generated the carry?
Yes, sir, yes, sir.
Sure. So similarly, you can generate the sum which is nothing but x XOR y XOR C out, as you can see. So it is 0, then this will be 0, 0, 1. And this one, then it is 0, then it is 1, 0, then it is 1. Is it fine?
Yes.
Oh, wait. Now what we have to do, sorry, what we have to do, we have to write j and k in terms of x and y. So if you have followed the last lecture, we need to convert these flip-flops, or we need to get the relation of j and k in terms of x and y. So we'll check qn and qn plus 1, and similarly we'll write the j and k flip-flop. So for that we need to make the excitation of j and k first, and then we'll first make the characteristic table of j and k flip-flop, and then we'll go for this excitation table. So I hope you remember. So j, k, qn, and then qn plus 1. So 0, 0, and it is, sorry, no, qn plus 1. Can anyone tell what is the output of this table, or should I write by
Zero.
myself?
Zero.
Okay, so I'll write whatever you're saying. 0,
One.
1,
Zero.
0,
Zero.
0,
One.
1,
One.
1.
Zero.
Recheck this.
Sorry, one. Yeah, doggle, no? One.
Yeah, 1.
Zero.
Yeah. So I'll repeat how it has come. So for when J and K both are 0, the state is nothing but Qn. When J and K are 0 and 1, the state will be always 1. Sorry, the state will be always 0. When J and K are 1 and 0, the state will always be 1. The next state I'm talking about, Qn plus 1. And when both J and K are 1, it will toggle. So the state will be Qn bar. So this is how we get 0, 0, and then this will always remain 0, this will always remain 1, and this will always be, this will toggle. So it is Qn bar. So now from this Qn and Qn plus 1, we'll write what are the values of J and K. So we have 4 values. So can you tell here also?
Yeah, it's 0 to 0. 0 x, I think. Just check
No.
once. 0, 0.
So yeah,
Yeah,
I'll
zero
direct
x.
I'll tell how it is coming. So there are 0, 0. There are two cases of 0, 0. One is here and one is here. So you can check in both the cases j is 0 and k is 0 and 1. So we should substitute k to don't care.
Next is 1x.
Yeah. So this is the method of getting this. So now we are getting 0, 1. So let me try some different thing. Yeah. So 0, 1 is, wait. Yeah. So give me a moment. I have joined. Yeah. So now it is 0, 1. What I was, yeah, 0, 1 and 0, 1. So this is,
1x.
yeah, wait. So this is 0, 1, and there is no 0, 1. So in this j is 1, 1, and x is don't care. So it is 1x. Then similarly for 1, 0, there are two cases. This is 1, 0, and this is
x1.
1. So it is x1, yeah, right. And for the last case, it is 1, 1, and this is 1, 1. So it is x and then
0.
0. Yeah. So similarly, now we'll approach, if I can, yeah, I can't shift it, but so you can see here Qn and Qn. So it is 0, 0, and it is 0, 0 here also. It is 0, 0 here also. So for all these three cases, what we will have is 0x, right? Is it fine?
Yes, yes.
So 0, 1 will always give 0, right? Oh, sorry. 0, 1 will give 1x. My bad. Then this is 1, 0, 1, 0 will give x and what? X and 1. Then it is 1, 1. It is x0. It is again 1, 1. It is x1. Then x1. Is it fine?
Yes, yes.
Fine. So now we'll make the k map to solve the final equation. So it will be First I'm writing for J. So it is Qn bar and Qn. This is X bar, Y bar. This is X bar, Y. X, Y. This is X, Y bar. So I will just write 0, 0, 0, 1. Then X, 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 X. So J will be, you can clearly see, it is nothing but this only, which is X, Y. Is it fine?
Yes, yes.
Now I'll write for K. Can you tell me the expression for K? You can make the K map and tell me what is that you are getting. So it is X, 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 then 1, 0, 1, 1.
2 expressions will get, I think.
Okay. So one is surely,
One is squad, other one is roll.
other one is what?
Roll on that corner, left and right.
One is this, right?
Other one is left and right. You can roll.
Yes. Wait, X, Y bar, X, Y. So you are saying one is this?
No, no, no. That's
Yeah,
the
fine. You,
this way.
right? Yeah.
Yes.
So the answer will be K is nothing but, if I try to write with some different thing, this is nothing but X5 and what was this? X5 bar. Uh, X and then for 1 1 it is X0 in last two steps. Oh yeah, yeah. So here is the problem. That is why we are getting weird answer. So it is 0 0. This is 1 1. So now I'll write again. It is X X X X and then 1 0 0 0. We'll only get a single quad. No, we'll not even get a code. We'll just get this. Okay, my bad. Let me rewrite it. It is getting confusing. Wait. Hmm. So if I try to write it, it will be X X X X and then 1 0 0 0. So we'll only get this, which is nothing but X bar Y bar. So K is X bar Y bar. Did you understand it?
Yes, yes.
So there must be some option. Oh yeah, option one is the answer. It is A. So this was quite a good question. It will help you in solving some problems in the competitive exams also. Is it fine? Shall I proceed? Shall I proceed?
Yes, sir.
Okay, fine. So if you have understood the concept of, okay, fine. So this is a basic question. It says it is a 8-bit serial in parallel outshift register. So it has a clock frequency of 2 megahertz, and the initial value of register is nothing but 8 times 0. And yeah, so initial value is this. So it is saying the time required. So time required is nothing but the frequency inverse and whatever the number of bits is given in the question. Oh, yeah. So this is a generic formula for serial in parallel out register. So we'll just substitute the values. It is nothing but 1 upon n is what? 8 bit and then frequency is 2 megahertz. Okay, I've written something wrong. Yeah, yeah. This n is into it. Right? So it is nothing but 1 upon frequency and the total number of bits. So it was quite basic and n is 8 in the question. So if I try to write, it is 8 by 2 to 10 power 6. This will get in microseconds and 8 by 2 is 4. The correct answer is option number C. Is it fine? It is quite basic. 。  . 。  . 。 . . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . 。 . . . . . There are a few more interesting questions of this kind in the later section of this. So maybe I'll just wrap up this and go ahead. Is it fine? Shall I proceed?
Yes, sir. Yes, sir.
Okay, fine. Yeah. So, show the previous question answer. This one. Uh, we're talking about this one. Okay, JK1. Yeah, sure. Here's the answer. This.
The answer page is next page.
Okay, this page. Okay, fine. So, shall I proceed now? Okay, so maybe you can try this by yourself. So, it is again a circuit. You can see it has a T flip-flop. So, again the states are getting just shifted, and the last state is nothing now. Earlier in the earlier question, the last state was nothing but Q4 is getting as an input of the first flip-flop. In this, Q4 bar is getting the input as the first flip-flop. So maybe you can tell me what is. Okay, I'll give you some initial hint. So it says that the initial state of the Johnson counter. So yeah, first of all, this circuit is called Johnson counter. So in Johnson counter, what we have is the last bit which is getting complemented is getting as an input of the first bit. So this is the main characteristic
After
of the.
after eight clock pulse, the Johnson counter set back to 0000.
Okay, fine. So I'm getting one answer as B, right? Since the time period is one, and you are saying after eight,
Yes.
right?
Mm. Mm.
Sure. Okay. So maybe you can try to solve this conceptually also. Like the initial state is given as 0, 0, 0, 0. This Q1, Q2, Q3, Q4. And we can see that the Q1 is nothing but Q4 bar if I try to write simple. And Q4 bar is Q1. Is it fine with all of you? Is it fine?
Yes, sir. The state would be 1000.
Yeah, so now the next state will be 1000 since this is Q4 bar.
One
So
one zero
now,
zero.
so yeah, this bar is getting here. Now this is 110 and then this bar. And then again one,
All
one, one.
ones.
Yeah. And since the initial state is
Zero
0,
one
will
one. 0111. 0011. 0001. Last zero.
yeah. So you can see it was the initial state. This was the first, second, third, and fourth. Then this was fifth. This was sixth. This was seventh. And after eight clock pulse, since the time period is one, so the correct answer to this question is option number B only. You are correct. Is it fine or yeah? So this is an important concept. Many questions in the competitive exams they ask that this is a Johnson counter and they don't even provide the circuit. They just say it is a Johnson counter and just tell us what is the delay. So one more thing that you need to add of Johnson counter is for a n-bit Johnson counter, it has two n states. So a 4-bit Johnson counter has 8 states. So from here you can also tell that it will come after 8 clock pulses. Is it fine? Should I repeat? I've done it quite quickly, so maybe I can make the arrows for you. This row is nothing but Q4 bar. So this again with some different ink. So this is getting barred over here. This is here. This is here. No toggling will happen. Yeah. So in the last step, the toggling is happening. You can see Q4 is getting barred again and again. Q4 bar we are getting as the input of the first input. So 0 is getting to 1, then 1, then 1 again. Then 1 is converted to 0. So toggling is happening here. Is it clear, Santosh? Q1 is nothing but Q4 complement. Toggling only. Is it clear? It's a T flip-flop, not a D flip-flop. Yeah. Okay, so I know it is a T flip-flop, but it is the bits are just getting shifted, so there is no toggling here. Okay, you are correct that it is getting just shifted, and the first bit is getting complemented. They are just getting shifted. No need to worry about the inside of the circuit. Yeah. So if you have understood this question, suppose a 4-bit, yeah. So maybe you can tell me this if you have understood the Johnson counter properly. So it says maybe I will give you some more options. Let's say 2, then ES, what are the 4, and FS, maybe 6. So in this, multiple answers are correct now. So this can be a gate multiple selection type question. So maybe you can tell me what is the answer to this question.
But which flip flop it is implemented, that also important to
So
calculate this.
yeah, so I have just said that they will just say that we have a 4-bit Johnson counter. So Johnson counter,
Which flip flop is used to implement 4-bit Johnson counter?
so Johnson
Flip
counter is
flop
always
not
implemented. Yeah, you can implement it by either D or either T flip flop. So you can use D flip flop if you are getting confused by T here. You can just use D flip flop. So I'll make a circuit of Johnson counter. Maybe you can take a D here. So 4-bit. Just the difference in the Johnson counter is the last bit is getting complemented. So this is Q4 bar. It is getting adding here. And then we have a clock. Is it fine? This is Q1, this is Q2, this is Q3. So we have uh, 6 options for this question. You need to tell me what are the correct answers. Which of the following state will not occur, it is saying. I'll give you maybe 2 minutes. It is easy.
two will not occur.
Okay, so one answer is 2 will not occur. Any
Five,
other answer?
five.
5 also. Okay. Any other answer? Anyone else with some answer? Okay, I'll do it if you're not getting. So it says the initial state is 1 1 1 1. Johnson counter is nothing but now this 1 1 1 and it is getting 0. 0 1 1, it is getting 0. 0 0 1, it is getting 0. 0 0 0, it is getting 0. 0 0 0, it is getting 1. So I hope it is clear. So 1 1 1, then 0 1 1 1. So I can make the arrow like this. Then 0 0 1 1, then 0 0 0, then this, then this, then this, and then again this 1 1 1 is getting to this. So if I try to write the decimal equivalent is nothing but 15. This is 7. This is 3. This is 1. This is 0. This is 8, right? Yeah. This is 12. This is 14, and this is 15. Yeah. So the states which are occurring are 0, 1, then 3, then 7, then 8, then 12, 14, 15. Yeah. So question has 7 is not the answer, 5 is the answer, then 3 is also there, 2, 4, 6. Yeah, 2, 4, 6 is not considered here. Wait, since it is a 4-bit counter, so let me erase these options. Yeah. So you are correct. B and D will be the answer if I frame this question like this. Is it fine?
Sir.
Everyone, is it
Yes.
fine? So just do a question, a quick exercise. I am giving you a 3-bit Johnson counter. So just tell me what are the possible states. You can do it maybe in 1 minute. It is a quite easy question. You can take initial state as either 0 0 0 or 1 1 1, whatever you want. So just tell me the number of states and the what are those states. You should write your answer in the chat box. I'll give you 1 minute.
Same 2 and 5.
Sorry?
Same 2 and 5.
I am saying that which state will occur. I'm not asking now will not. I'm saying will occur.
7 to 3, 3 to 1, 1 to 0, 0 to 4, 4 to 6, 6 to 7.
7 to 3, 3 to 1, 1 to 0. Then?
0 to 4, 0 to 4, 4 to 6, 6 to 7, 7 to
Okay,
6
so
back.
fine. So 1 1 1 is getting 1 1. I'm doing it quite fast now. So this is 0 0 and this is 0. Oh, sorry. This will be 1 0 0. This will be 1 1 0. Now again 7. So 7 to 3, then 1, then 0, and then again 4, 6, and then 7. Yeah. So these are the possible 6 states. I've already told you for an n-bit Johnson counter, we have 2 n states. So we will have 6 states. And we don't have 2 and 5 for the same question. Is it fine with everyone? Please do respond if it is fine. Okay. So yeah. So if you have understood the concept of LFSR, maybe you can try to do this question. You just need to write the polynomial equation of this. I will give you 2 minutes. I hope you know what are maximum length sequences. I'll tell you. Maximum length sequences are nothing but x plus 1. This n is the highest order. One more answer can be x to the n minus n, x to the power n minus 1, x to the power n minus 0. So you are getting such expression, they will get a maximum length sequence. First of all, tell me the polynomial representation of circuit 1 and circuit 2. Anyone? Uh, should I do it or you're doing it? Uh, Anyone with the answer? Okay, fine, I'll do it. So I just told LFSR the first bit will always be x to the power 0, which is 1. This will be x to the power 1, this will be 2, this will be 3, this will be 4. Same with this. So XORed is for the first circuit, x3 and sorry, x cube and x to the power 4 are getting XORed and they are getting to the input. And for the second circuit, you can see x to the power 0, this is 1, this is 2, 3, and then 4. So 4 and 1 are getting XORed. Is it fine? Am I not audible or you are not responding?
Yes, sir.
Am I
Fine.
audible?
Clear, clear,
Yeah.
clear.
Okay, okay. So I just wrote that what polynomials can generate the maximum length sequence. So it should be in these type of polynomial. One can be this and one can be this. So here n equals to 4. You can see there are 4 bits. So if I put n equals to 4, so the one of the answer will be x to the power 4 plus x plus 1, and the second answer will be x to the power 0 plus x to the power 4 minus 1 and plus x to the power 4 minus 0. So it will be x to the power 4 plus x cube plus 1. So these two possible cases can generate the maximal length sequence. So one of the equation is this only and one is this. So the correct answer to this question will be option number D. Is it fine?
Yes, sir. Yes, sir.
So, okay. So if it is fine, then just tell me the answer to this question. Okay, okay, I'll repeat. Uh, is this part fine that how I have generated the polynomial equation? Santosh, you can open your mic and talk. It is fine.
Yes, sir.
Okay, so the polynomial equation, the maximum length is generally generated by x to the power n, which is the maximum sequence, then x plus 1. So this is a general representation. So this type of polynomial can generate the maximum length sequence. And for certain cases, which is when the bits are even, as you can see, there are 4 bits. There is one more answer to the same question, which is x to the power n minus n, x to the power n minus 1, and x to the power n minus 0. It is nothing but x to the power 0 plus x to the power n minus 1 plus x to the power n. So if I write it, it is x to the power n plus 1. Is it fine till here?
Yes, sir.
So I'm just putting n equals to 4. So one answer would be x to the power 4 plus x to the power plus x plus 1, and one answer would be x to the power 4 plus x cube plus 1. Fine.
Yes, sir.
So both of the equations we are getting from the given circuit. So that is why the answer is option number D. This is a general representation for the generic circuit. So if you are getting a general question, you just need to check this. If you are getting this equation, it will generate the maximum length sequence. Is it fine?
Yes, sir.
So now you can approach this question. First, you need to write the equation and then just tell me it if it is maximal or not. Any answer?
Answer C.
Okay, I'll just repeat what I told. You need to check that this is the general representation. You should not consider this as a secondary option. This is for only even cases. And the question here says it is odd, 5 bit. So maybe if you want to recheck now, I'll just do it. Yeah. Still C? I'll get general representation. Okay, so can anyone tell me the polynomial representation of this? This is x to the power 0, which is 1. This will be 1, 3, 1, 3. So it is nothing but x5 getting resolved with x4 plus 1. So these two are eliminated, and since it is not equals to x to the power 5 plus x plus 1, so it is not a maximal sequence. So the correct answer would be option number D. Is it fine?
Yes, sir.
Okay. So fine. Yeah. So now try to do this question. I've tell you enough concept of LFSR. Just tell me what will be the period of this LFSR. Yes, I have done this question earlier also, so maybe you can repeat it. It will clear your concepts. First, make the circuit of this LFSR and then tell me the period. You can type your answer in the chat box. Any answer? Anyone? We have done it, I guess, before in this lecture only. I'm audible, right? Okay, so one is answer 7. Yeah, correct answer is 7 only. Okay, I don't know why it took so much time to answer this. It was quite easy. Let me remind you. So it says it is a 4-bit LFSR. So we'll just make 4-bit LFSR. This will be x to the power 0, x to the power 1, x to the power 2, 3, and then 4. The polynomial representation is x cube plus x square. So we have already done this question earlier in some other format. So I took these bits as P, Q, R, S, and I said that P is nothing but Q XOR R. And I started with, I guess, 1 1 1. So here I can start with 0 0 0 0. So this is P, Q, R, S. Once you will do the question, it will be wait, yeah, it will be 0 0 0, and then sorry, I need to start it with 1 1 1 only. 1, then it will be 0. 1, 0, 1, 0, it will be 1, 0. So this is getting repeated after 1, 2, 3, 4, 5, 6, and then 7. So yes, these are right answer. Is it fine? We have done it earlier also. Is it fine with everyone?
Yes, sir. Yes.
Okay, fine. If it is fine, then you can try this question. No. Okay, fine. I'll do this by myself. So it is a delay line circuit. So a delay line circuit is nothing but a cascade connection of odd numbers of NOT gates and should be odd. So it is a concept of delay line circuit, and it is a cascade connection of odd numbers of NOT gate, and the total delay or the frequency of the circuit, which we can say is F out, it is always equals to 1 upon 2n and tau PD. So this is an important relation where F out is the frequency given, then n is the number of inverters or number of bits or flip-flops you can say. Then what is left? Yeah, tau PD is the propagation delay. The question says that it has a delay of, so tau PD is given as 0.64 millisecond. Then how many number of flip-flops n we need to find, and the frequency given is 1.25 megahertz. So can anyone quickly do the calculation and tell me the answer? What are they getting? So you need to calculate n, which is 1 upon 2 into f out into tau PD, 2 into, what is this? 1.25 megahertz, which is 10 to the 6, and then tau PD is 0.64 into 10 to the minus 3. Can you tell me what is this number coming? You can use calculators. Okay, 800. Fine. I'm not rechecking if it is coming 800. So the correct answer to this question is option number B. Is it fine? This was a numerical problem. Shall I proceed? Okay. So now, okay, this is also a good question. So it says in the following diagram, the register A and B were loaded with the certain bits. So this is A and this is B. The flip-flop was initially reset. So it was initially reset, so I'm writing it as 0. And after the 8 clock pulse, what will be the loaded sequence in register A? Okay, fine. So we'll just start the question. So register A is initially 00, 4 times 0, 1001. This is 1001 and 0001. So it is given in the question and initial Ci minus 1, which is initially the flip-flop is reset. So I'm just writing all the possible cases. Uh, AI, then BI, maybe here is the clock. Initially, what is this? It is a full adder, so C, uh, maybe I can write this as Q, which is Ci minus 1. You can see here, initially it is 0, and then I can write sum and carry. Is it fine with everyone till here? 3, 4, 7, and then 8. So after 8 clock, it is asking that what will be the output sequence. So I'll write the output sequence of every term, maybe. Okay, I can make it here. So A is initially, sorry, I'll write it in the backward way. So first it will go 1, then 0, then 0, then 1, then 0, 0, 0, 0. There is 1, 0. Is that fine with everyone? Any doubts in this? Please respond if you have any doubts. Okay. So as you can see, this is a serial output register. So what we are getting is in the first clock pulse, this 1 and this 1 will get as an input. And then in the second clock pulse, this 0 and this 0 will get as an input. Okay, so I should write this as 1. Wait, my bad. In the first clock, 3, 4, 5, 6, 7, 8. So you can now you can relate that how this A and B. I've just written A in the backward sense here and B in the backward sense here. Is it fine now? Mm,
Yes, sir.
okay. So Ci minus 1, it is say that the flip-flop was initially reset. So Ci minus 1 was nothing but Q only. So I have written the first value as 0 only. Now we'll do the sum and carry. So you know for a full adder, the sum is, you can check, it is AX1, so it is 0 and the carry is 1. Now you can see after every state, it is a T flip-flop. So toggling will happen if Q is 1 or the Ci minus 1 is 0, then the toggling will not happen. So earlier it was 0 and this Ci will now get here since there will be no toggling. Is this step clear? This is quite important. Is it clear? Anyone? Is it not clear? I can repeat. You can just tell me. Okay, fine. I hope this A and B are clear from my side. And A and B are just a backward sequence since they are getting inserted like this. And what I have done is I have initially the question says that the output of the flip-flop it resets. So I have written C minus 1, which is the initial state, it is 0. Now I've just converted the sum and carry. So sum will be 0 and 1 for this particular case. Now since this is a T flip-flop, you know, if Q is 1, then the output is Qn bar. If Qn is 0, then the output remains Qn, right? So here you can see Q is 0, right? Right? Please respond, whosoever has asked the doubt. Yeah. So this Q is 0, so the toggling will not happen. So the earlier carry will now come here. That is why I have written the same answer, same carry as 1. Is it fine now? Okay, so now I'll just do 0, 0, 1. So sum will be 1, carry will be 0. So now the toggling will happen since the carry is the previous state is 1. So this 0 will get converted to 1. Is it fine now? This step is quite important. If you don't understand this step, you will not understand the whole question. Is it clear now? Yeah. So I'll just maybe write a bit upwards since it is getting shifted. So this was 0, 0, 1. This was 1, 1, 0. It will be 1 now. So 0, 0, 1 will again give 1, 0, I guess. Yeah. Again the carry will be 1. So 1, 0, 1 will give 0, 1. Then there is 1, so the carry will get toggle. 0, 1, 0 is 1, 0. Carry will not toggle. So carry will not toggle. 0, 0, 0 will be 0. And carry will not toggle. 1, 0. Is it fine? Is this table clear to you? Everyone, please respond. So is it clear to all of you? Or should I repeat? Uh, Rajini and Santosh, is it clear?
Yes, sir.
Okay. So as you can see that it is saying that after the 8 clockers, what will be the loaded sequence in register A? So register A is nothing, it is getting loaded with the sum. You can see, maybe I can use some different things. So it is loaded with the sum and it will get loaded backwardly. So the correct answer to this question will be SI only in the backward sense. So the correct answer is 1, 0, 0, 1, 0, 1, 1, 0. Which is option? Is it there any option? Yeah, option number B. It is quite good question. So if you did not understand the question, I can repeat. Just let me know. And if it is clear, so you can write in the chat box that it is clear. Okay, so the last part. So the question says that after 8th clock pulse, what will be the loaded sequence in register A? So register A is getting loaded with this sum. You can see this SI is going here. So first this SI will go here, then this SI will go here, and then so on. Do you understand this?
Yes, sir.
So the correct answer will be the backward arrangement of this SI. So it is 1, 0, 0, 1, 0, 1, 1, 0. So I've written it here only. Is it fine now?
Yes, sir.
Yeah, so the correct answer is option B. Shall I proceed to the next question? Okay, fine. So now most of the questions will be done by you only, I guess. Yeah, so it is again a uh, cascade node connection question. So maybe you can do it. I will give you 2 minutes. So the question says in that circuit diagram, the output frequency is 10 kilohertz. The desired output frequency is 10 kilohertz. How many number of flip-flops are required or inverters are required to cascade? And the propagation delay is given as 5 nanoseconds. Yeah, there is one trick in this question that it is two flip-flops. So you know that every flip-flop, the frequency gets halved in every cycle. I hope you know this. Is it clear to you earlier only? So F out will be Fn by 4. Is it clear this part? This is the trick in this question. Rest question is similar. You will just use what you will use and will be nothing but 1 upon 2 and tau PD. Sorry. F will be nothing but 2 and tau PD. You need to calculate this n. So can anyone calculate and tell me the answer? This is 5 nanoseconds. Then what else? F out is input is 4 F out. So what is the F given in the question? 4 kilohertz. So can anyone let me know what is the answer? This is 9 nanoseconds. This is 10 to the power 3. No, sorry. 10 into. Okay, so you are getting 2499. Are you sure? Let me recheck the calculation if I don't remember it. This is 10 to the power 4, this is 10 to the power minus 5, so it will be 10 to the power 5 upon, there will be one more 10. This will be 10 to the power 4 upon 4. So this is nothing but 10 up 4 into 10 to the power 3. This will be 2.5, 2500. Yeah. So since I have already told you this inverter should be odd in number. You're getting the answer is 2500, but since we need the inverters to be odd, the correct answer will come as 2499, which is option number C. Okay, yeah. So if the inverters will not be odd, there will be no oscillation. I'll try to explain. Yeah, maybe here. So let's suppose we have two inverters and we have three inverters. Suppose I've applied the input as 1 to both the cases. So here you can see the invert of this will be 1, sorry 0, and then invert of this will be 1, right? Please, whosoever asks the question, respond quickly because we have few more problems. Yeah. So what it is doing it is just storing this one, right? And if I do the same here, it is 1 0 1 0. So now it is getting 0. So it is regularly oscillating. So for oscillations, n should be odd. Did you understand this part? This 0 is now getting as an input, so it will again and again be getting oscillated. That is why this should be odd. So let me proceed to the next problem. Okay, so it is quite lengthy, so I'll do it by myself. So it says that it is a 8-bit Johnson counters. So 8-bit Johnson counters means 16 states. So it says that it is initially sequenced with this 1, 2, 3, 4, 5, 6, 7, 8. So it is saying that in the decimal representation, what will be the mean value? So I'm just writing all the possible states. So sorry, yeah. So the first state will be, and what is happening? First state will be. I hope it is clear. I'm doing it quite fast. Zero. Okay, I'm writing rest of the states here 0, 0, 0, then 5, then is it fine? All the possible states, there are 16 states. Is it fine? Okay, so I'll now convert them to the decimal equivalent of the, since it is asking the mean value of the counting state. So this is 0, this is 2 to the power 8, which is, oh sorry, 7, this is 128, this is 128 plus 64, it is 192, I guess. This is 192 plus 32, it is 194. Maybe you can apply the calculator. This is 192 plus 60, sorry, 32. It's getting 224, I guess. Then 224 plus 16, it is 240. Then plus 8, it is 248. Then plus 4, it is 252. Then 254, then 255. Now, what is this? This is 127, I guess. Hmm. This is 60 something. 3. If I'm not wrong, this is 31. This is 15. This is 7. This is 3. This is 1. I don't know if you can recheck if I have written all the values correctly. So what I'll do, I'll add all these value and divide it by 16 to find out the average. So 128 plus 192 plus 224 plus and so on till this last number is 1. Maybe you can use your calculator and tell me the answer quickly. Okay, I'll use. Just tell me quickly what is the answer. Uh, 28 plus 192 plus so on. Okay. 16. I'm getting 2040 and then I'm divided by 16. So yeah, I'm getting 127.5. I hope you all are getting this. The correct answer is option number C. Is it fine? Shall I proceed? Please respond. Shall I proceed? We have only 5 minutes left, so do let me know. Fine, so I'll proceed. So it says what will be the output of after two clock pulses if the bit sequence 1010 1 1 is serially entered into a 4-bit parallel out shift register, and the initial states are initially clear. So it is again the same question. Initial states are clear. Now it is getting shifted serially. So this 1 1 0 1 is getting shifted serially. So first this 1 will get inserted, then this 0, then this 1, then this 1. So initially in the first state this will be 0 0 0 and this 1 will get inserted here. Now the next state will be 1 0 0 and this 0 will get inserted here. Next state will be 0 1 0. This 1 will get inserted here. Next it will be 1 0 1 and this 1 will get inserted here. Is it fine? Any doubts in this?
No, last state, which one get inserted in MSB, sir? Right, leftmost.
So, okay, let me try to change the color.
I think that is 0.
So it is, if you see, it is 1 1 0 1. So this 1 is getting inserted here, this 0 is getting inserted here, this 1 is getting inserted here, and this one is getting
Okay, okay,
inserted here.
okay.
So this is the first clock pulse, second, then third, and then fourth. The question says what is the output after 2 clock pulses? So this is the output 0 1 0 0. So which is option number 4. Is it fine?
Yes, sir,
Yeah.
yes, sir.
So you can try this question now. Maybe you can tell me the answer quite quickly. So initially it is set to 111 and this 1010 is applied to the input. And it is asking after 3 clock pulses. Just let me know what is the answer coming. Side by side. Okay, previous answer this. Is it fine, Santosh? Okay. So the answer to this question is, can anyone calculate? Has anyone calculated? After 3 clock pulses, the output will be this. Has anyone calculated? It is coming out as 0101. Is it fine or do I need to repeat it? How I've done it? We have only two,
Question,
3 minutes left.
hello, hello,
Yeah, yeah.
am I audible?
Yeah,
In
yeah,
this
you are audible.
question, it's first initially set to 111. Then
Yeah.
how again the next data bit is applied to the input? This is also initial state, that is also initial state, 111 and 1010. Both are initial
No,
state to the
no,
register or
no. The
what?
data 1010 is getting serially. So this 0 is getting inserted in the first clock pulse. Then it is getting shifted. Then this 1 is getting inserted in the second clock pulse. Then this 0 in the third. Then this 1 in the fourth.
Oh,
So,
initially it is 111. Later on, serially one by one, this
yeah,
data
yes.
bit is inserted. Okay.
Yeah. So after third clock pulse, it is getting 0101. Is it fine?
Yes, sir. Yes, sir.
So quickly do this question now. I have already told. So it is initially 1100. So it is saying after four clock pulses, what will be the output? Just let me know. This is XNOR gate. Okay, I'll also do it side by side. So this is 110. 1, 2, 3, 4. It is asking. Let's our PQRS. It is RX XNOR S. 0 will give 1, 111, 0, 0, 1, 1, and 1, sorry, 101, it will give 1. Water flow, it is 100. Is it fine? Yeah. So these are quick questions which you need to do. So Yeah. So if you have any more query, okay, there is one more question. It says a shift register with its complement Q bar at the last state connected to the D input. So we have read it. It is a Johnson counter. A Johnson counter is also known as a
Twisted ring counter.
yeah. So it is one. Yeah, I'm done with the questions, I guess. So I hope this session will be useful. You can try this question at your home with 1010. Okay, you are asking my email. Sure, I'll type it in the chat box. I have written it in the chat box. You can mail me if you have any queries. So with this, we can end the session, I guess. So, okay, can you please show the answer for the T flip-flop question? Which is the T flip-flop? Uh, this one. Sorry, does not have a T flip-flop. Where's the T flip-flop? Maybe you can email me. I'll send you the PDF, or you can get it in the drive. So since we are out of time, I'll send you this PDF. Is it fine? Yeah. So we'll meet next week at the same time from 6 to 8 on Monday. Till then, take care. Bye bye.